So this is the first video dealing with reaction mechanisms, and in this video I'm just going to go through basically most of the theory. So again, just a bit of wording. There's a bit of text on here that I'll try to explain, and some definitions you might want to get down. But why don't we get started and we'll see what we come across. So if you recall collision theory, what needs to happen for a reaction to proceed at an appreciable rate, that is, at a measurable rate? Well, you probably remember that we have to have collisions. So molecules need to collide. Okay, so that's very important. But you also have to have sufficient energy. And that's the activation energy. We already defined that. So particles have to be at or above activation energy and collide. And finally, they have to have an appropriate or optimal orientation. That is, the colliding molecules, the molecules that are going to react, that collide, have to have their electron clouds interacting in and around a region that will be conducive to electron transfer or change in bonding. So those are the main things that have to happen for a reaction to take place. So we're going to focus in on this one for the time being, collisions. So let's just proceed. Now we're going to have a look at a billiard ball table, because this is actually a pretty good analogy for trying to see the types of collisions that are happening and the frequency of these collisions. So let's first of all have a look at this setup. So here we go. So we're going to slow it down. Now we can start seeing some of the collisions. You can try to keep track of the different types of collisions you can see, if you like, and see what happens. And here we go, fast again. So when it's going fast, it's actually happening pretty quickly, and it's hard to really get a sense of the different types of collisions. So let's watch that again, and here I'm going to focus in on a couple of collisions, and you should hopefully see what I'm trying to get across here. So here we go again. Alright, so focus on a yellow stripy ball. And so you can see that is not really an effective three-particle collision. Okay, so coming up, we're going to focus in on a blue stripy ball. And again, I think you see that's probably more conducive. That's probably a more appropriate three-particle collision. So in that second video, I just wanted to highlight that you can actually have three particles hitting each other, but again, the orientation does come into play. And so the second three-particle collision was probably a collision that would give rise to a reaction, because the electron clouds were much interacting to a much greater extent. All right, so back to this billiard ball analogy, and just a few things we want to make sure we realize. So, did you see any 14 ball collisions? That's all the balls on the table at once, and that's obviously a great big no. That's not going to happen. So what are the most frequent types of collisions you saw? Well, even though it was pretty hard to tell, the most frequent were definitely these two ball collisions. And we did see the odd three-ball collision, but they were much less frequent. And so if you think about it, if you extend it, how likely is it that five balls will collide simultaneously? Well, that's unlikely. How about 11? Highly unlikely. And so I'm just trying to get across the point that most reactions, just like collisions on a billiard ball table, do not occur necessarily as written. When we get complex equations, you'll see one in a minute, the reality is it's probably not actually taking place in that particular fashion. It's not a 5-ball collision or an 11-ball or 11-particle collision. It's something simpler, and that's really what mechanisms are all about. So case in point here is a reaction. 5 iron 2 ions react with 1 permanganate ion and 8 hydrogen ions. So what's the likelihood of this reaction occurring in one step or occurring as written? Well, that's not going to happen, because we would require a 14 particle collision. 14 particle collision, so that's simultaneous collision with all particles having sufficient energy and in optimal orientation. And I think you would agree that's to have that all come together at once, so that 14 particles with their electron clouds interact in optimal orientation with sufficient energy. The likelihood of that is very, very low. Certainly not at an appreciable rate, at appreciable speed. It may happen, but it's going to happen so infrequently that the rate of reaction would be exceptionally low. So this is really what reaction mechanisms are all about. So here is a few definitions for you. So complex reaction proceeds at a measured rate, probably occurs by a series of simpler steps, and this is what a reaction mechanism is. So each step in a mechanism is called an elementary process or elementary step. And so reaction mechanism then is the series of elementary processes involved in a chemical reaction. The elementary process then is a reaction whose rate law can be written from its molecularity, and molecularity is the number of species that must collide to produce the reaction represented by an elementary step in a mechanism. So all of those definitions are kind of intertwined. So let's kind of separate those out and see if we can sort of appreciate again what a mechanism is. So first of all, in terms of molecularity, so elementary steps include these different types of collisions. So a unimolecular collision, a single molecule is broken down. So this is basically a one-particle collision. And how can you break things down? Well, UV radiation is often one way to break things down. This happens in the atmosphere. For example, chlorine gas is broken down into 2 chlorine radicals. Also ozone, this is how ozone breaks down. O3 is broken down into oxygen molecule and an ozone or oxygen radical. So a single molecule, unimolecular. It doesn't really involve a collision of particles, but you can still separate particles out that way. Bimolecular, 2 molecules makes sense. And so hydrogen iodide is a good example here, because in both directions this is a bimolecular process. The formation of hydrogen iodide from hydrogen and iodine, H2 colliding with I2, 2 particles. The decomposition of hydrogen iodide, if I wrote that backwards, would basically be the same thing. I could write it this way, hydrogen iodide plus hydrogen iodide. There's my 2 moles reacting, yield H2 plus I2. So in both directions, that's a bimolecular process. And finally, trimolecular, 3 molecules are consumed or react. And again, example of this is the synthesis of water, 2 moles of hydrogen, 2 molecules of hydrogen plus 1 molecule of oxygen. So all 3 of these types of steps or processes are considered elementary or simple. So they're simple and they are likely to occur as written because they're so simple. And as we saw in the billiard ball scenario, the biomolecular process is probably the most common. Unimolecular, not as common, and certainly trimolecular, not as common. So a lot of elementary processes involve biomolecular steps. So, for most reactions, the individual steps cannot be detected, so a reaction mechanism is just a theory. So this is what chemists who study kinetics do, is they try to put together these reaction mechanisms. It's not that easy. It takes a fair bit of trial and error, but this is what they try to do, to try to explain reactions that have a measurable rate but appear on the surface to be too complex to occur in that fashion. So you don't have to determine mechanisms. What you have to be able to do is sort of be able to analyze them. We'll get to that in a bit. So of particular importance here is that the elementary process, the exponents of the rate law, are the same as the stoichiometric coefficients for each reactant in the chemical equation, that elementary step. So from an elementary step, you can write the predicted rate law, which is the rate law. Now, predicted rate law, what does that mean? Well, let's have a quick look here. So here's this, back to this crazy reaction. We can write a predicted rate law, as it says, based on the stoichiometric coefficients in the equation. So for this one, R equals K, and I'm going to predict that I have Fe2 plus to the power 5 times permanganate ion, that's the power 1, times the hydrogen ion to the power of 8. Okay, so that's the predicted rate law, but we can probably we would quickly realize that's not going to be the actual rate law. Fifth order with respect to hydrogen ion, eighth order or fifth order with respect to iron 2 ion, eighth order with respect to hydrogen ion. Those are very high reaction orders. 13th order overall. Okay, highly unlikely that that's going to happen that way. So, but that said, this we can write a predicted rate law. So when we have simpler steps, elementary processes, we can write the predicted rate law, which is actually the rate law for the mechanism. Remember, this is one step in a series of steps. If we know that it's going to set the rate law, or set the rate, we can write the rate law for the overall mechanism. So in a mechanism comprised of elementary steps, we write the actual rate law for the mechanism. Consider. So here's back to ozone. So if we know this reaction is determined as setting the rate for a mechanism, the actual rate law is going to be R equals K times the concentration of ozone. And that's the power of 1. So this mechanism is first order overall and first order in ozone. So the point being, if you know something about the mechanism, and the mechanism is made up of elementary processes, you can write a rate law. You actually don't need to do all the experimentation we've talked about previously. Here's the second example. So we have the formation of water from hydrogen and oxygen. So again, this is an elementary process. This is a trimolecular process. It sets the rate in a mechanism, so the overall rate law is going to be R equals K H2 squared O2. Again, the coefficients set the rate law. They become the exponents. And that's really all I wanted to say about reaction mechanisms to begin with. So to quickly summarize, a mechanism is a series of elementary steps. An elementary step is a simple step, a simple reaction involving 1, 2, or 3 reactants at most. And if you know something about the reaction of action, if you know that the one of the elementary steps sets the rate of the mechanism. You can write a rate law for that entire mechanism based on that one elementary process. So we're going to look at some experimental applications of reaction mechanisms in the next video. So for the time being, that concludes this video.